mass of each molecule into the square of its velocity. According to him, matter consists of small particles which do not touch one another, since otherwise a diminution of volume by lowering of temperature could not be explained. The matter of heat exists between these particles. The hotter a substance is, the more of the matter of heat does it contain. In the investigations into the specific heats of various substances, carried out along with Laplace, Lavoisier further proved that for a like increase in temperature, substances do not take up like quantities of the matter of heat. Lavoisier knew that by the addition of heat, ice is first converted into water, and the water then into steam. Hence, gases contain most of the matter of heat. This is what we should understand when he says that his air pure consists of the acidifying principle and the matter of heat. During combustion, the former unites with the combustible substance, and the matter of heat is liberated. It produces light and heat. Lavoisier also termed the matter of heat calorique. Lavoisier's views with respect to the heat liberated during combustion, although not quite accurate, are also of great importance. He considered that when a solid substance, phosphorus, burned in gas, oxygen, and the product of the combustion was solid, phosphoric anhydride, the disengagement of heat was due to the condensation which the gas had undergone, in order that it may become solid. If the product was gaseous, carbonic anhydride, he attributed the disengagement of heat to the alteration of the specific heat. He advanced the general view that the heat of combustion must be greatest when two gases unite to form a solid substance. How correctly he understood the application of these fundamental ideas is shown by his mode of explaining the lowering of temperature produced by dissolving salts in water. Lavoisier assumed, as we do, that it is the change of state of aggregation which occasions the absorption of heat. He showed further that the evolution of heat which occurs on mixing sulfuric acid with water is accompanied by a decrease in volume, and that both maxima coincide, so that theory and experiment agree. Ladenburg. It may be said, therefore, that Lavoisier laid the foundation for the modern thermochemistry. Lavoisier also occupied himself with organic chemistry, or the chemistry of life products, and made a beginning toward a scientific study of it by devising a method of analysis by which these bodies could be burned, and the water and carbon dioxide which were formed measured. He heated a known weight of the substance with a known weight of red mercury oxide, and weighed the carbonic acid and water produced. He knew the oxygen content of the mercuric oxide, and so could ascertain how far this supplied the carbon and hydrogen with the oxygen they required, and how far this was furnished by the compound under investigation. Lavoisier in this way determined the composition of alcohol. However, the whole system of quantitative organic chemistry was too young for Lavoisier to anticipate the nicety with which Liebig later could handle these methods of ultimate analysis. He considered his experiments to be merely confirmatory of his system, the composition of sugar a mere incident. Organic bodies in general he regarded as oxides of a radical, which might itself contain hydrogen and carbon, or in some cases these together with nitrogen, sulfur, and phosphorus. Lavoisier adhered to Boyle's definition of an element. With him, an element was any substance which could not be further decomposed. The metals and the most important nonmetals were ranked among the elements, and compound bodies like the alkalis, ammonia, and the earths were numbered among these also, but not without considerable uncertainty being expressed as to their elementary nature. Oxygen, also recognized as an element, became, because of its part in combustion and its capacity for combining with so many other elements, the center point of the antiphlogistic system, which indeed owed its inception to the knowledge of the behavior of other elements toward oxygen. The importance which Lavoisier attached to this gas is clearly shown in his theory of acids, in which he explained the properties of acids by the hypothesis of the acidifying principle being oxygen, the name of which, a Greek word meaning I generate acid, still bears witness to this view, and in the statement the bases which combine with acids also contain oxygen. The composition of a large number of compounds, oxygens, acids, and salts, was thus rightly interpreted, the phlogistic hypothesis having regarded as simple the substances belonging to the first two of these classes. The views of Lavoisier and his disciples with respect to elements and compounds are to be found in the treatise entitled Méthode de nomenclature chimique, which was published by Lavoisier conjointly with Guyton de Morveau, Berthollet, and Fourcroy in 1787. This work, in conjunction with the Traité élémentaire de chimie, 1789, changed the existing language of chemistry and shaped the course of progress still pursued. In the first mentioned treatise, all substances are divided into elements and compounds. To the former belonged, in addition to light and heat, oxygen, hydrogen, and nitrogen. These formed the first class. The second group, containing the acid-forming elements, sulfur, phosphorus, and carbon, to which were added the hypothetical radicals of hydrochloric, hydrofluoric, and boracic acids. The third class comprised the metals, the fourth the earths, and the fifth the alkalis. But Lavoisier considered the elementary nature of the last of these as so improbable that in the Traité élémentaire de chimie he no longer included them among the elements. For the nomenclature of the latter, the old names of the metals and some of the non-metals, for example, soufre, phosphore, etc., were retained, while Lavoisier's new names for others of the non-metallic elements, for example, oxygen, hydrogen, azote, were introduced. Next came the binary substances, consisting as they did of two elements. The acids occurred in this class. Their names were in each case composed of two words, of which the first was common to them all and indicated their character, acide, while the second was a specific name indicating the element or radical occurring in each. Thus we have acides sulfurique, carbonique, phosphorique, nitrique, etc. Two acids containing the same element or radical were distinguished by the different termination of the specific name, that containing the smaller proportion of oxygen receiving the termination -ux, whereby such names as acides, sulfuro, nitro, etc. were obtained. Hydrochloric acid was called acide muriatique, and the existence of oxygen in it was assumed, while oxygen was supposed to be present in still greater quantity in chlorine, the acide muriatique oxygene. The names of the binary substances of the second group, for example, of the basic compounds containing oxygen, were formed in a manner exactly similar. For these, the general designation oxides was introduced, and to this word the specific name was appended in the genitive. For example, oxyde de zinc, oxyde de plomb, etc. The remaining binary compounds were distinguished as sulfur, phosphorus, carbon, etc. compounds and received the class names sulfures, phosphures, carbures, etc. Compounds of the metals with one another were called alliages, alloys, the expression amalgams being retained, however, for mercury alloys. With regard to the ternary compounds, the salts alone need to be mentioned. They obtained their class names from the acids from which they were derived, and were called accordingly sulfates, nitrates, phosphates. The termination -ate became -ite when the salts were derived from the acid poorer in oxygen instead of from that richer in oxygen. The name of the base was appended, for example, sulfate de zinc, de barite, etc. This system of nomenclature embodies the principles and constitutes the basis of the chemical nomenclature now in use. Studies of the new nomenclature were published by Shearer, 1792, who made an attempt to Germanize the new terms, Eimke, 1793, who sought to reconcile the old and the new views in his Synonymicon. Arzt, 1795, Spalding, who published a work at Hanover, New Hampshire, in 1799, in which he followed de Morveau, but adapted the name septon for nitrogen, and septic acid for nitric acid as proposed by Samuel Mitchell of New York, Severin, 1807, and Ritter, 1808. It is amusing to note here that Richard Chenevix, a London chemist, published a critical examination of the nomenclature of the French neologists in 1802, in which he quoted Balthazar Sage's remark that oxygen signified the son of a vinegar merchant. When the nature of the theoretical views held during the phlogistic period is compared with that of the ones accepted at the time of Lavoisier's execution, it will be understood why a new era, that of quantitative chemistry, or as Fourcroy termed it, the French chemistry, dates from him. As mentioned, the teachings of Lavoisier gradually became recognized in France, a reward which Lavoisier himself had the satisfaction of witnessing, and also gained ground in England, and through the influence of Klaproth in Germany, where his works were translated, so that at the beginning of the 19th century, chemists had almost universally given in their adherence to the antiphlogistic chemistry. Lavoisier not only overthrew the old theory, but it is to his credit that he introduced a new one in its place, and it is perhaps advisable to state here the most important heads of his theory, Lautenberg. 1. In all chemical reactions, it is the kind of matter alone that is changed, while its quantity remains constant. Consequently, the substances employed and the products obtained may be represented by an algebraic equation, which, if there is any unknown term, this may be calculated. In the process of combustion, the burning substance unites with oxygen, whereby an acid is usually produced. In the combustion of the metals, metallic calces are produced. All acids contain oxygen, united, as he expresses it, with a basis or radical which in inorganic substances is usually an element, but in organic substances is composed of carbon and hydrogen, and frequently contains also nitrogen or phosphorus. If these three statements be contrasted with the views of the phlogistians, i.e. with the theories which prevailed prior to Lavoisier, we shall appreciate the reformation introduced by him into chemical science. The direction of chemical thought was entirely changed, and the facts hitherto ascertained appeared in a new light. Chemistry now had the basis of a correct theory, and what was of greater value, a knowledge that theories could be deduced only from the weight relations of actually occurring reactions. To quote Venable, there were to be no baseless and delusive dreams for the future, although mistakes might be made in the interpretation of facts. Further, the grand division into elements and compounds had been effected, and a suitable nomenclature had been devised, capable of any expansion demanded by increase of knowledge. The balance, too, had been introduced as the instrument by which precision and accuracy were to be attained, and the great arbiter of the fate of theories. True progress now became possible, and the century which has since passed has seen this science develop and grow, until men have come scarcely to dare put a limit to its possibilities. Those three investigators, Guyton de Morveau, Claude Louis Berthollet, and Antoine-François Fourcroy, who in conjunction with Lavoisier furnished the basis of a scientific nomenclature, and also contributed to the development of chemistry by their other works, are next to be considered. Louis Bernard Guyton de Morveau, 1737 to 1816, was a zealous propagandist of the new chemistry, and upon his election as a deputy in 1791, he endeavored to render the chemical knowledge he had acquired and its practical application of assistance to France. He aided in founding the École Polytechnique, in which institution he subsequently accepted a professorship, and with Marais and Durand as co-authors, he published a comprehensive textbook on chemistry in 3 volumes, entitled Éléments de chimie théorique et pratique, 1777. Claude-Louis Berthollet, who was born at Talloires in Savoy in 1748, was one of the most distinguished of the many contemporaries and successors of Lavoisier. He became an anti-phlogistonist in 1786, and from that time until his death in 1822, he conducted valuable chemical researches. His important experimental investigations were in connection with the composition of ammonia, the properties and nature of chlorine, the production of bleaching compounds from chlorine, and the composition of hydrogen sulfide and hydrocyanic acid. He observed that solutions of chlorine in water gave off bubbles of oxygen when exposed to the action of light, while hydrochloric acid remained. Lavoisier had considered that this acid was a compound of the radical murium with oxygen, and consequently, Berthollet explained the phenomenon referred to by regarding chlorine as oxymuriatic acid, that is, a higher oxygenated product of murium. Berthollet discovered that ammonia is composed of hydrogen and nitrogen, and after convincing himself that hydrogen sulfide and hydrocyanic acid contained no oxygen, he opposed the dictum that oxygen was the principle of acidity. Berthollet was the author of the following works: Éléments de l'art de la teinture, 1791. Researches sur l'huile de l'affinité, 1801, and Essai de statique chimique, 1803. The last mentioned treatise was an exceedingly important contribution to theoretical chemistry, for it exerted a powerful influence on the question of chemical affinity. Berthollet's doctrine of affinity will be discussed in the next chapter. Antoine-François de Fourcroy, 1755 to 1809, deserves mention as an organizer, author, and teacher. He was an active expounder of the antiphlogistic doctrine and propagated the new chemistry by means of articles and treatises. He was the author of the following works: Leçons élémentaires de histoire naturelle et de chimie, 1782. Éléments de histoire naturelle et de chimie, 1789. Mémoires et observations de chimie, 1784. Philosophie chimique, 1792, and Systèmes de connaissances chimiques et leurs applications aux phénomènes de la nature et de l'art, 1801. Fourcroy's experimental work served to pave the way for biological chemistry, and his joint investigations with Vauquelin furthered the knowledge of organic compounds. Another important representative of chemistry in France at this time was Louis-Nicolas Vauquelin, 1763 to 1829, who succeeded Fourcroy as professor of chemistry to the medical faculty in 1809. To Vauquelin is owed the discovery of chromium, 1797, and beryllia, 1797, the former of which he found in lead spar and the latter in beryl. His work on the separation of platinum, palladium, discovered by Wollaston in 1803, rhodium, Wollaston 1804, iridium, Tennant 1803, and osmium, Tennant 1803, is also worthy of note. Vauquelin's investigation on the metals of the platinum group were carried out with the assistance of Fourcroy, and it is likely that they preceded Smithson-Tennant in the discovery of iridium. In his researches in organic chemistry, Vauquelin discovered quinic acid, asparagine, and camphoric acid. He was the author of 2 works, Instructions sur la combustion de végétaux, la fabrication de salines, de la cendre gravely, 1794, and Manuel de Essayeur, 1812, both which passed through several editions. The leading chemists of Great Britain and Sweden at the time when Lavoisier began his attack on the phlogistic theory strongly opposed the new chemistry. Cavendish, Priestley, Bergman, and Scheele were unable to accept it, but Black renounced the old doctrine in 1791 and was followed by Dickson and Richard Kirwan. The latter's interesting essay on phlogiston and the constitution of acids, 1787, deals with the transition period from the old to the new theories and was translated into French by Mademoiselle Lavoisier. Among the lesser celebrities in the science in England, Lubbock subscribed himself to Lavoisier's views as early as 1784, while Peart and Pugh attempted to prove the existence of phlogiston as late as 1795. In 1810, a small essay on combustion was published in Philadelphia by a Mrs. Fulham, wherein the phlogistic and antiphlogistic hypotheses are proved erroneous. This is merely mentioned on account of its being one of the earliest American contributions to the subject. Martin Heinrich Klaproth, 1743 to 1817, first professor of chemistry at the University of Berlin, was characterized by the accuracy with which he carried out his investigations. The quantitative method of research was developed and improved by him, and he thereby helped on the recognition of the cardinal principles advocated by Lavoisier. After Klaproth had become satisfied with the correctness of the antiphlogistic doctrine by testing the reactions which took place in combustion and calcination, he became one of its devoted adherents, and his example led many other German chemists in the same direction. Klaproth discovered uranium, 1789, titanium, 1794, cerium, 1803, and zirconia, 1789, and investigated the new elements chromium, beryllium, and tellurium, discovered by Müller von Reichenstein in 1782. He was particularly active in analytical and mineralogical chemistry, and introduced many improvements of analytical methods. Klaproth was, in fact, a true investigator in every sense of the word. In reporting the results of analysis, he published the actual figures obtained, thus introducing a new custom which made it possible to subject results to correction or criticism. His works are Chemische Untersuchung der Mineralien zu Carlsbad, 1790, and Beitrag zur chemischen Kenntnis der Mineralkörper, 1795 to 1815. The latter is a collection of his papers published in the Memoirs of the Berlin Academy and in the Chemische Annalen für die Freunde der Naturalien. He also published the Chemisches Wörterbuch, 1807 to 10, 5 volumes, 1815 to 19, 4 volumes, a French edition of which appeared in 1811, and edited the third edition of Friedrich Grand's Systematisches Handbuch der Chemischen Chemie, an excellent treatise, first published in 1787 to 90. From 1803 to 10, Klaproth was on the board of editors of the Neues Allgemeines Journal de Chimie, which was started in 1798 by Scherer. In this connection, it should be mentioned at that time about 12 chemical periodicals were being published in Germany, 3 in France, 2 in Italy, 2 in Belgium, 1 each in Holland and Sweden, and 2 in England. These journals exercised the greatest influence upon the enlargement and diffusion of chemical knowledge, and they show the extent to which chemistry was fostered during the last decades of the 18th century. End of section 13. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com.
Section 14 of the Science, History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a recording by Joanne Crosby. The Science, History of the Universe, Volume 4, edited by Francis Rolt Wheeler, Chemistry, Chapter 10, The Atomic Theory and the Work of Davy. A desire ingenite in the human mind to find an explanation of natural phenomena by the aid of speculations respecting the ultimate constituents of matter resulted in guesses and ideas concerning atoms. In olden times, without, however, the evolution of an exact chemical atomic theory. With respect to the hypothesis of the ancient philosophers regarding the constitution of matter, the following estimate by Clifford will suffice in this connection. Quote, "From the earliest times that man began to form any coherent idea of the world at all, they began to guess in some way or other how it was that it all began and how it was all going to end. Modern speculations are attempts to find out how things began and how they are to end by consideration of the way in which they are going on now. A great number of people appear to have been led to the conclusion that the modern theory of the molecular constitution of matter is very similar to the guesses which we find in ancient writings, Democritus and Lucretius. It so happens that these ancient writers did hold a view of the constitution of things which in many striking respects agrees with the view which we hold in modern times. The difference between the ancient and modern views is mainly this. The atomic theory of Democritus was a guess, and no more than a guess. Everybody around him was guessing about the origin of things, and they guessed in a great number of ways. But he happened to make a guess which was more near the right thing than any of the others." End quote. The conception of atoms had, up to the close of the 18th century, been almost entirely the property of the metaphysician and the mathematical physicist, and had assisted in extending their sciences. With the exception of Cernate and Boyle, chemists had aided little in its formation and less in its establishment, nor had they derived inspiration from it for the proper founding of their own science. For more than a century, they had been following the igneous fatuous of a false theory of combustion and a most elusive hypothetical phlogiston. The close of the 18th century found them engaged in a bitter strife over these theories, and too fully occupied to think of much else than the destruction of the old beliefs and the adaptation of the new. The mastermind of Lavoisier, who had wrought this revolution, was busied with the greater work of reconstruction and dealing a little with the hypothesis which could not be directly proved by experiments in his laboratory, was laying broad and strong foundations of the new chemistry. Consequently, the works of Bergman, Scheele, Priestley, Black, Cavendish, Macquer, and others did not treat of atoms and their moving forces, except in an occasional indefinite reference to some sort of particle. Yet the chemists were the very one required to undertake the scientific development of the atomic hypothesis and to establish it as a theory by discovering a series of facts which were connected together by it and found in it a simple explanation. In 1783, the English chemist Kirwan went so far as to refer to affinity as the force which holds atoms so intimately together that simple mechanical means are insufficient to separate them, while his countryman Higgins, writing in 1790 on the composition of sulphurous and sulfuric acid, expresses the opinion that the atom of sulfur is combined with one atom of oxygen in the first, but with two atoms in the second. It is in the view of this statement, and others similar to it, that some have regarded Higgins as the real originator of the modern atomic doctrine. However, Higgins restricted his attention to a small number of compounds. His conceptions were not consistent with the fact. He regarded those weights of elements which combine to form the simplest compounds as in general equal, and he made no attempt to seek confirmation for any theory he had in the laboratory. For long, the common consent of the public opinion was given the undivided honor, due to the discoverer of the great atomic generalization in its modern aspect, to John Dalton. Before the establishment of the chemical atomic theory could be brought to completion, however, it became necessary to fix the significance of the term chemical proportions, according to which simple substances unite to form compound bodies. And an important part of this question was solved by two chemists prior to Dalton, Richter and Proust. Jeremiah Benjamin Richter, 1762-1807, published in his De Usu Mathiosin Shumia, 1789, Auffangsgründe der Stochemistrie oder Messkunst chemischer Elemente, 1742-1794, and Über die neueren Gegenstände der Chemie, 1791-1802. The results of researches made mainly while employed as a works chemist in Berlin. The last two mentioned treatises contain the conclusion which he drew from his work upon the proportions by weight in various compounds. Richter looked upon chemistry as a branch of applied mathematics and exhibited all the distressing qualities of a person possessed by a fixed idea. He spent his life in seeking arithmetical regularities in the weights of acids and alkalis neutralizing each other, and in finding them in spite of their non-existence. Nevertheless, he managed to make discoveries of the highest importance. He not only noticed but also correctly interpreted the fact that when two neutral salts decompose one another, the resulting salts are neutral. To quote his conclusions, concerning that very common experience that two neutral salts on decomposition again produce neutral compounds, I could draw no direct inference other than that fixed quantitative relations must exist between the constituents of the neutral salts. If a solution of two compounds is so constituted that neither of them, as long as it remains in the solution, exhibits the peculiar characteristics it had before solution. Example given: the reactions of an acid or of an alkali, then such a solution is called saturated or neutral, or also a neutral compound. When two neutral solutions are mixed and a decomposition ensues, the newly formed products are also, almost without exception, neutral. Hence it follows that if the combining ratios in the original compounds be known, those in the newly formed compounds are also known. End quote. C.F. Wenzel, 1740-1793, at an earlier date, 1777, had demonstrated that acids and bases combine in constant proportions, but had failed to note the persistency of the neutrality in the double decomposition of the neutral salts. Richter deduced from the maintenance of neutrality when one metal precipitates another from a neutral solution, a relation Bergman had observed but which he interpreted in terms of another theory, that the quantities of two metals which dissolve in the same amount of acid also unite in their oxides with the same amount of oxygen. Therefore, he established that quantities of two substances which are equivalent in one reaction are also equivalent in the others. He was the originator of stoichiometry, or the art of chemical measurement, which has to deal with the laws according to which substances unite to form chemical compounds. Notwithstanding the fact that Richter's treatise contained such important discoveries, these remained unrecognized until Fischer published a table of the relative affinities of bases and acids, founded on the values Richter had obtained in his translation of Berthollet's Recherche, made in 1802. Berthollet accepted the law of proportionality and gave an account of it in his Essai de Statique Chimique, in which he reprinted Fischer's note. Thus, Richter's work, which at the time of its publication had been almost completely ignored, became more widely known and appreciated. Louis-José Proust, 1755-1826, although a Frenchman by birth, conducted his most important researches in Madrid, where he settled after 1791. The work for which he is celebrated was the result of a series of questions which Berthollet had advanced. The two works of Berthollet on affinity, Recherche sur les lois de l'affinité and Essai d'une statique chimique, were particularly directed against false views of affinity and the misuse of the so-called affinity tables of Geoffrey Bergman and others. He contended that affinity was by no means a simple force, and easy to determine or measure, but was influenced by temperature, physical state, cohesion, and especially by mass. The latter largely determined the course of chemical reactions. He went further, however, and from the correct premises of the influence of mass on the chemical effort produced, Berthollet drew the erroneous inference that mass had an influence, not only on the amount of change, but also on the kind, producing a continuous variation in the ratio in which the constituents are united in a compound. He asserted the variability of the composition of chemical compounds, the possibility of combination between constituents, and all sorts of continuously varying ratios. None of the other leading chemists of the day were able to concur with his views as to the lack of any fixity or constancy of proportion in chemical compounds. Yet they raised no objection, probably owing to Berthollet's reputation, and it remained for Proust to attack the theoretical conclusions of his eminent contemporary. Proust's numerous papers in his controversy with Berthollet appeared in the Journal de Physique between the years 1802 and 1808. The lucidity of the arguments employed, the variety of the experimental work described, and the freedom and keenness of the style rendered these papers, which deal exclusively with the distinctly dry subject of quantitative analysis, most interesting reading even now. Proust proves that substances formed under the most varied conditions have a fixed composition, and he shows that Berthollet's examples of variable composition were all cases of mixtures. This involves him in the necessity of discriminating between mixtures and compounds, an undertaking the difficulties of which he fully realized and with which he dealt in a manner very much like that still resorted to for the same purpose. Von Meyer. In 1799, Proust had proved the constant composition of native and artificial carbonate of copper, and had enunciated the general principle of which this constituted an example. Of greater importance than these were observations he made upon the two compounds iron forms with sulfur and the two stages of oxidation shown by tin. He further investigated the compounds of antimony, cobalt, nickel, and copper, and throughout he found that, vary the conditions and relative masses at pleasure, the oxides and sulfides produced always have a definite composition. To be sure, an element might combine with oxygen or sulfur in two proportions, but each has a compound of definite proportions. Proust showed the error which underlay the old method of determining the quantity of oxygen and oxides, of estimating the metal and calculating the oxygen by difference, proving that in many cases the bodies so examined were not oxides at all, but compounds containing hydrogen, hydroxides we now call them. He moreover demonstrated that many of the bodies, on the analysis of which Berthollet had based his generalizations, were not simple at all, but mixtures of substances themselves of perfectly definite composition. So accurate were his analytical investigations, and so logical his reasoning, that Berthollet was overcome at every point. The law of definite chemical proportions as we now have it was the fruit of his persevering labors. This law is one of the fundamental principles of chemistry. It is expressed by the greatest teacher of chemistry as follows. Quote, if one substance is transformed into another, then the masses of these two substances always bear a fixed ratio to each other. If several substances react together, then their masses, as well as those of the new bodies formed, always bear fixed proportions to each other. End quote. Oswald, Outlines of General Chemistry. Undoubtedly, if Proust had calculated the results of experiments on the composition of binary compounds, sulfides, oxides, in another manner from what he did, he would have discovered the law of multiple proportions, but the propounding of this is due to Dalton. John Dalton, 1766-1844, was born at Eaglesfield in Cumberland, the son of a poor weaver. Endowed with natural aptitude and an indomitable will, he used all possible opportunities for the study of mathematics and natural philosophy. From 1781 to 1793, he taught school, instructed and lectured at Kendal, devoted all the time and energy he could spare to scientific investigations, chiefly meteorological. In 1793, he went to Manchester as tutor of mathematics and natural philosophy at a Presbyterian college. Though he resigned his post 6 years later, he remained in Manchester to the end of his life, earning his living as a private teacher and devoting himself uninterruptedly and earnestly to scientific research. The earliest researches of Dalton on the expansion of gases by heat and their absorption by liquids were of considerable influence on his later chemical work, as it was through them that he acquired the experimental skill which led to the discovery of the law of multiple proportions, which, with the conception of the atomic theory, which arose from it, dates from 1802. On November 12, 1802, Dalton read a paper entitled An Experimental Inquiry into the Properties of the Several Gases or Elastic Fluids Constituting the Atmosphere, on which he found the first example of the law. In determining the amount of oxygen in the air, the following experiment was performed. Quote, if 100 measures of common air be put to 36 of pure nitrous gas in a tube 3/16 of an inch wide and 5 inches long, after a few minutes the whole will be reduced to 79 or 80 measures and exhibit no signs of either oxygenous or nitrous gas. If 100 measures of common air be admitted to 72 of nitrous gas in a wide vessel over water, such as to form a thin stratum of air, and an intermediate momentary agitation be used, there will, as before, be found 79 or 80 measures of pure azotic gas, nitrogen, for a residuum. If, in the last experiment, less than 72 measures of nitrous gas be used, there will be a residuum containing oxygenous gas. If more than some residuary nitrous gas will be found. These facts clearly point out the theory of the process. The elements of oxygen may combine with a certain portion of nitrous gas, or with twice that portion, but with no intermediate quantity. In the former case, nitric acid is the result. In the latter, nitrous acid. But as both these may be formed at the same time, one part of the oxygen going to one of the nitrous gas, and another to two, the quantity of nitrous gas absorbed should be variable, from 36 to 72%, for common air, end quote. With regard to this experiment, Roscoe says, quote, in the memorable case in which Dalton announces the first instance of combination in multiple proportions, the whole conclusion is based upon an erroneous experimental basis. If we repeat the experiment as described by Dalton, we do not obtain the results he arrived at. We see that Dalton's conclusions were correct, although in this case it appears to have been a mere chance that his experimental results rendered such a conclusion possible. End quote. The first of the observations of Dalton which furnished the experimental basis for the atomic theory consisted in the determination of the composition of 2 hydrides of carbon. Dalton writes, quote, it was in the summer of 1804 that I collected at various times and in various places the inflammable gas, marsh gas, obtained from ponds. End quote. He found that marsh gas, like olefiant gas, ethylene, contains nothing but carbon and hydrogen, and that these 2 substances, termed light and heavy carbureted hydrogen, respectively, showed a simple multiple ratio between the weights of the constituent elements, namely, in carbureted hydrogen from stagnant water, 4.3 of carbon were combined with 2 of hydrogen. In olefiant gas, 4.3 of carbon were combined with 1 of hydrogen. This regularity induced him to investigate other compounds in the same direction. Thus, in the case of carbonic oxide and carbonic acid, he found that, for the same amount of carbon, the ratios of oxygen present in these were again, respectively, as 1 to 2. His convictions that there must be a law underlying these simple relations scarcely necessitated any further accretion after he had encountered similar simple numeric proportions and the results of his analysis of nitrous oxide, nitric oxide, nitrous acid, and nitric acid. In essence, the anhydrides of the last 2 and the oxygen compounds of sulfur. He had, therefore, demonstrated that when different quantities of one element combine chemically with one of the same quantity of another, these amounts stood in a simple relation to one another, a relation which could be expressed with whole numbers. The law of multiple proportions was thus discovered. It had indeed been deduced from experiments, which were of necessity not very exact, but this was to be expected from the condition of analytical chemistry at that time. Dalton next sought an explanation of the numerical relations he had discovered, and this was afforded him by the atomic hypothesis. For instance, he had but to assume that in carbon monoxide, 1 atom of carbon was combined with 1 of oxygen, and in carbonic acid, 1 atom of carbon was united to 2 of oxygen. Upon this basis, Dalton erected his atomic theory, which may be detailed from statements in his New System of Chemical Philosophy, 1808-1810, as follows. Number 1. All bodies of sensible magnitude are constituted of a vast number of extremely small particles or atoms of matter bound together by a force of attraction, which, as it endeavors to prevent their separation, is called attraction of cohesion. But as it collects them from a dispersed state, is called attraction of aggregation, or more simply, affinity. Number 2. The ultimate particles of all homogeneous bodies are perfectly alike in weight, figure, etc. In other words, every particle of water is like every other particle of water. Every particle of hydrogen is like every other particle of hydrogen, etc. Number 3. No new creation or destruction of matter is within the reach of chemical agency. All the elements we can produce consist in separating particles that are in a state of cohesion or combination and joining those that were previously at a distance. Number 4. The ultimate particles of all simple bodies are atoms incapable of further division. These atoms, at least viewed along with their atmospheres of heat, are all spheres and are possessed of particular weights which may be denoted by numbers. Number 5. If there are two bodies which are disposed to combine, then their combination takes place by atoms. Number 6. In an elastic gas, each particle occupies the center of a comparatively large sphere and supports its dignity by keeping all the rest, which by their gravity or otherwise are disposed to encroach upon it, at a respectful distance. The methods by which Dalton determined the relative atomic weights from the proportions by weight in which the elements unite to form compounds falls next to be described. To accomplish this, the first thing necessary was to settle the number of atoms in a compound. According to Dalton, this number is to be sought for, in general, in the simplest possible ratios. In estimating it, he started from the following principles. Number 1. When only one compound of two elements is known, this is composed of an atom of the second order. Number 2. When two compounds are known, the one consists of an atom of the second and the other of an atom of the third order. Number 3. When three compounds are known, one atom of the second and two atoms of the third order must be assumed. How did Dalton now proceed to the determination of the atomic weights? In essence, the relative weights of the smallest particles. In the first place, it was necessary to choose a unit for comparison. As unit, he assumed hydrogen with the atomic weight equals 1, and he referred all the other atomic weights to this. To fix the others, he then applied his first principle. At that time, only one compound each of oxygen and of nitrogen with hydrogen was known, namely water and ammonia, respectively. Therefore, the atomic weights of oxygen and nitrogen can be determined directly from the composition of these compounds. In this way, Dalton found them to be 7 and 5, respectively. He checked the numbers so obtained by the proportions of the oxygen and nitrogen in the oxygen compounds of nitrogen. He was acquainted with 4 of the latter. In nitric oxide, he found 7 parts of oxygen for 5 of nitrogen. Its atom was, therefore, the atom of the second order, derived from these elements. In nitric acid, according to his view, there were 14 parts of oxygen for 5 of nitrogen, or 2 atoms of the former gas for 1 of the latter. In nitrous oxide, 7 parts of oxygen were combined with 10 parts of nitrogen, and in this he therefore assumed 2 atoms of nitrogen and 1 of oxygen. Nitrous acid, however, is supposed to contain 10.5 parts of oxygen for 5 of nitrogen, and in it he might have assumed 2 atoms of nitrogen and 3 of oxygen. He preferred, however, to regard the substance as a compound of nitric acid and nitric oxide. Likewise, he found in ethylene 5.4 parts of carbon for 1 of hydrogen, and in marsh gas the same quantity of carbon for 2 of hydrogen. On this account, he regarded ethylene as consisting of atoms of the second order and assumed the atomic weights of carbon to be 5.4. Carbonic oxide likewise consisted of atoms of the second order, since he found in it 7 parts of oxygen for 5.4 of carbon, while carbonic anhydride, and atoms of the third order, because it contains 14 parts of oxygen for 5.4 of carbon. As the analytical methods of Dalton employed were liable to many sources of error, it was out of the question that the results he obtained could be accurate. However, it was he who propounded the principle of the determination of the combining weights of the elements, and this work brought him everlasting fame. Dalton's atomic theory, generally speaking, was favorably received by chemists. Thomas Thomson, 1773-1852, who founded the first chemical laboratory for general instructions in Great Britain while professor in the University of Glasgow, became its devoted supporter, and his System of Chemistry, 1807, made it known to the general public. In 1808, Thomson supplied an observation of his own in support of the law of multiple proportions. Dalton's attempts at a graphic presentation of the ultimate particles of various substances must not be forgotten. The symbols he used to represent the atoms of the elements and to indicate the constitution of chemical compounds, as well as his relative weight values, are here given. This system of notation never came into general use, owing to the introduction of a simpler system by Berzelius sometime afterward. To quote his own inference, it appears that there are two oxalates of strontium, the first obtained by saturating oxalic acid with strontium water, the second by mixing together oxalate of ammonia and muriate, chloride of strontium. It is remarkable that the first contains just double the proportion of base contained in the second. End quote. He also investigated the potash salts of oxalic acid. Quote, oxalate of potash readily crystallizes in flat rhomboids, commonly terminated by dihedral summits. The lateral edges of the prism are usually beveled. At the temperature of 60 degrees, it dissolves in thrice its weight of water. This salt combines with an excess of acid and forms a superoxalate, long known by the name of salt of sorrel. The acid contained in this salt is very nearly double of what it contained in oxalate of potash. Suppose 100 parts of potash, if the weight of the acid necessary to convert this quantity into oxalate be X, then 2X will convert it into superoxalate. End quote. Similar research was done by W.H. Wollaston, 1766-1828, who, by experiment, found that in the two compounds termed subcarbonate of potash and carbonate of potash, the proportions of carbonic acid relative to the same amount of potash were 1 to 2. He also showed that supersulfate, bisulfate, of potash contains, quote, exactly twice as much acid as is necessary for the mere saturation of the alkali present. End quote. These contributions prove the applicability of the law for salts, and the importance of the relation thus made evident was, in general, realized by the chemists of the day. Figure 20, Dalton's graphic presentation of the elements. Simple. Figure 1, hydrogen, relative weight 1. 2, azote, relative weight 5. 3, carbon or charcoal, relative weight 5. 4, oxygen, relative weight 7. 5, phosphorus, relative weight 9. 6, sulfur, relative weight 13. 7, magnesia, relative weight 20. 8, lime, relative weight 23. 9, soda, relative weight 28. 10, potash, relative weight 42. 11, strontium, relative weight 46. 12, baryte, relative weight 68. 13, iron, relative weight 38. 14, zinc, relative weight 56. 15, copper, relative weight 56. 16, lead, relative weight 95. 17, silver, relative weight 100. 18, platina, relative weight 100. 19. Gold, relative weight 140. 20. Mercury, relative weight 167. Binary. Number 21. An atom of water or steam composed of one of oxygen and one of hydrogen, retained in physical contact by a strong affinity and supposed to be surrounded by a common atmosphere of heat. Relative weight 8. 22. An atom of ammonia composed of one of azote and one of hydrogen. Relative weight 6. 23. An atom of nitrous gas, one azote plus one oxygen, relative weight 12. 24. An atom of olefiant gas, one carbon plus one hydrogen, relative weight 6. 25. An atom of carbonic oxide, one carbon plus one oxygen, relative weight 12. Ternary. 26. An atom of nitrous oxide, two azote plus one oxygen, relative weight 17. 27. An atom of nitric acid, one azote plus two oxygen, relative weight 19. 28. An atom of carbonic acid, one carbon plus two oxygen, relative weight 19. 29. An atom of carbureted hydrogen, one carbon plus two hydrogen, relative weight 16. Quaternary. Number 30. An atom of oxynitric acid, one azote plus three oxygen, 26. 31. An atom of sulfuric acid, one sulfur plus three oxygen, relative weight 34. 32. An atom of sulfurated hydrogen, one sulfur plus three hydrogen, relative weight 16. 33. An atom of alcohol, three carbon plus one hydrogen, relative weight 16. Quinquennary and sextenary. Number 34. An atom of nitrous acid, one nitric acid plus one nitrous gas, relative weight 31. 35. An atom of acetous acid, two carbon plus two water, relative weight 26. Septenary. Number 36. An atom of nitrate of ammonia, one nitric acid plus one ammonia plus one water, relative weight 33. 37. An atom of sugar, one alcohol plus one carbonic acid, relative weight 35. It is now necessary to discuss the position which Davy and Gay-Lussac, among others, held respecting Dalton's atomic theory, as well as to narrate their services to chemistry in general. Humphrey Davy, the son of an engraver, was born at Penzance in 1778. The family circumstances were somewhat impecunious, and at the age of 17 he was apprenticed to a surgeon apothecary in his native town. Figure 21. Preparation of nitrous oxide. At the age of 20, he was placed in charge of the laboratory of the Pneumatic Institute at Bristol, founded by Beddoes for the application of gases to the treatment of diseases. Davy's environments here were most propitious for a successful career of scientific research. His laboratory was well furnished and was supported by the subscriptions of scientific men. He had plenty of time at his disposal, and the age was one of discovery and rapid progress in science. His experiments related chiefly to nitrogen monoxide or nitrous oxide, and in a short time he published his, quote, researches chemical and philosophical, chiefly concerning nitrous oxide and its respiration, end quote. His courage and determination were well proved by these experiments. The effect of this gas, supposed to be poisonous, were tried upon himself. He discovered its anesthetic action. He then subjected himself similarly to the action of hydrogen, nitrogen, and carbonic acid. In 1801, Davy left Bristol to become a lecturer at the Royal Institution, and 2 years later was elected Fellow of the Royal Society. He was soon a necessary figure in the fashionable life of the day. His auditors of the Royal Institution were numbered by the thousand. His name was on everybody's lips. It was Coleridge who said, quote, "I attended Davy's lectures to increase my stock of metaphors," end quote. He was knighted in 1811 and created baronet in 1812. A terrible mining disaster at Felling brought him an invitation from the governors of the mine to investigate the conditions of such occurrences. And after an extended investigation into the nature of marsh gas and its different admixtures with air, he projected his well-known safety lamp. This is but one instance out of many of his scientific insights being turned to material advantage. Davy was elected president of the Royal Society in 1820 and died at Geneva in 1829. At the Royal Institution, Davy had at his command an excellent electric battery, and as he had for some time considered that the most needed step in chemistry was the decomposition of some of the substances then regarded as elementary, he thought that this was the most promising means for the solution of the question. In 1790, Galvani made his well-known experiment, and 10 years later, Volta invented his electric cell. These were important elements in the inquiry which went to correlate chemical and electrical phenomena, and the perception that a close relation existed between electrical force and chemical reaction spread rapidly at the beginning of the 19th century, after the decomposition of water into its constituents by the galvanic current had been proved by Nicholson and Carlisle in 1800, and that of salts into their bases and acids by Berzelius and Hisinger in 1803. The most important of the many and varied observations on the deportment of chemical compounds when subjected to the actions of the current, however, were made by Davy, and his discoveries entitled him to be regarded as the pioneer of electrochemistry, as well as one of the most brilliant chemists the world has ever seen. Davy was among the first to investigate the question of the decomposition of water. This work was begun in 1800. In his Bakerian lecture, delivered before the Royal Society in 1806, the subject of which was "On Some Chemical Agencies of Electricity," is found an investigation concerning the products of the electrolysis of water. Besides hydrogen and oxygen, there was also formed acid and alkali. Davy states this as a fact. Quote, "The appearance of acid and alkaline matter in water, acted on by a current of electricity at the opposite electrified metallic surfaces, was observed in the first chemical experiments made with a column of Volta." End quote. The problem requiring solution then was to ascertain whether the acid and alkali were derived from the water, and if not, whence they came. Davy therefore proceeded to carry out his electrolysis in vessels of various materials, and to show that the products mentioned, the acid and the alkali, were due to the glass, or to the matter dissolved in the water, or to the air itself. If the water, distilled in silver, was electrolyzed in gold vessels in an atmosphere of hydrogen, the acid and alkali did not appear. To give his own description, quote, "I repeated the experiment under more conclusive circumstances. I arranged the apparatus as before, gold cones and water distilled in silver vessels. I exhausted the receiver and filled it with hydrogen gas from a convenient air holder. I made a second exhaustion and again introduced hydrogen that had been carefully prepared. The process was conducted for 24 hours, and at the end of this time, neither of the portions of the water altered in the slightest degree the tint of litmus. It seemed evident then that water, chemically pure, is decomposed by electricity into gaseous matter alone, and to oxygen and hydrogen." End quote. He next investigated the decomposition of salt solutions and found confirmation of the statements of Berzelius and Hisinger. But he proceeded with still greater circumspection and sought to follow up the phenomena more exactly. All the means were at his command, and he did not hesitate to avail himself of them. Figure 22. Davy's apparatus for electrolysis of water. A and B electrodes. C strands of asbestos. Direct observations proved to Davy that hydrogen, the alkali, the metals, etc., are separated by means of the current at the negative pole, and oxygen and the acids at the positive pole. From this he concluded that the former substances possess a positive, while oxygen and the acids possess a negative electrical energy. That in this case, as usual, the oppositely electrified bodies attract each other, and that, in consequence, the positive substances separate at the negative pole and vice versa. And this assumption, Davy had arrived at an explanation of the phenomena of decomposition observed in the galvanic circuit. But he proceeded a step further and endeavored to refer all chemical combinations and decomposition to similar causes. According to him, the heat observed in certain cases of decomposition were manifestations of electricity. On November 19, 1807, Davy delivered an account to the Royal Society of his most recent work on the nature of the alkalis. He had made an attempt to decompose them by the electrolysis of their aqueous solutions, but without success. He had then passed a powerful current through solid potash fused over a flame and had observed a most intense light at the negative pole, due probably to the combustion of the element he was seeking. And his next experiment was decisive. To give his own description, quote, a small piece of pure potash, which had been exposed for a few seconds to the atmosphere so as to give conducting power to the surface, was placed upon an insulated dish of platina, connected with the negative side of a powerful battery. The positive pole was brought in contact with the upper surface of the alkali. On passing the current, the potash began to fuse at both its points of electrical action. There was violent effervescence at the upper surface. At the lower or negative surface, there was no liberation of elastic fluid, but small globules having a high metallic luster appeared. End quote. And he had treated soda in the same manner with similar results. Quote, it appears, he said, that in these facts there is evidence for the decomposition of potash and soda into oxygen and two peculiar substances. End quote. To these two peculiar substances he gave the names potassium and sodium. In 1808, Davy had decomposed hydrochloric acid by means of potassium, and in this way had obtained hydrogen and potassium chloride, the latter of which he had also prepared by burning potassium and chlorine. He proved in 1809 that the chlorides, muriates, of the metals are not decomposed by heating them with calcium metaphosphate or with silicic anhydride, but the decomposition at once begins when aqueous vapor is conducted over the mixture. Davy considered that Henry's hypothesis furnished the explanation of these experiments, and that hydrochloric acid could only be separated as soon as the quantity of water necessary for its existence was supplied. About the same time, Gay-Lussac and Thenard showed that water is produced as well as silver chloride by the action of this acid upon silver oxide. And as formerly, they assumed that this water was already present in the hydrochloric acid. They then effected the synthesis of the acid by exposing a mixture of chlorine and hydrogen to sunlight. On this occasion, they advanced a complete theory regarding hydrochloric acid and chlorine, by means of which they were able to explain all their experiments. According to them, hydrochloric acid was a compound of an unknown radical, muriaticum, with oxygen and water. Chlorine, on the other hand, was anhydrous hydrochloric acid combined with more oxygen. Davy next sought to find the oxygen which was assumed to be present in oxymuriatic acid, but by no means whatever could he abstract the oxygen from this compound. A succession of electric sparks produced no effect, neither did strongly ignited carbon. If the gas were oxidized, muriatic acid, phosphorus, and sulfur might be expected to combine with the oxygen and liberate the muriatic acid. No such result had been obtained, however, and the oily liquids which were produced only yielded muriatic acid on the addition of water. The oxymuriatic acid, when passed over oxides of potassium, barium, and other metals, produced muriates, with evolution of precisely that amount of oxygen contained in the oxides. Referring to this experiment, Davy remarks, quote, it is contrary to sound logic to say that the exact quantity of oxygen is given off from a body not known to be compound when we are certain of its existence in another. End quote. He therefore explained these facts by regarding oxidized muriatic acid as an elementary substance, and muriatic acid as its compound with hydrogen. But chemists hesitated upon accepting his views. Davy maintained that this element, to which he gave the name chlorine, resembled oxygen in many respects and, in a limited sense, was also to be regarded as an acidifier and supporter of combustion. The work of Davy was clear and brought conviction, and by 1820 his theory of the nature of chlorine was generally accepted. But oxygen could no longer be regarded as the sole acid-making principle, and this necessitated a new theory of acids. A French saltpeter manufacturer, Courtois, in 1811 discovered a particular substance in the soda obtained from sea plants. He related his observation to Clement, who showed the body in question to Davy. Davy soon demonstrated its elementary nature, and Gay-Lussac, after a complete investigation of iodine, as he termed it, and its compounds, succeeded in showing its marked likeness to chlorine. Bromine was discovered by Ballard in 1826 in the mother liquid of seawater. Hydrofluoric acid resisted all attempts to isolate its radical, but Ampère's suggestion that it was constituted similarly to muriatic acid found general acceptance. From his observation that iodic anhydride was devoid of acid properties, but acquired them after combination with water, Davy arrived at the conclusion that hydrogen and not oxygen was the acidifying principle in the latter compound. Hydrogen, in his opinion, was an essential constituent of all acids. The assumption that hydrated acids and salts contained water or metallic oxides together with acid anhydrides he held to be unproven and unnecessary. The French chemist Dulong expressed himself in a like manner after an investigation of oxalic acid and its salts. And the former he looked upon as a compound of hydrogen with carbonic acid, while in the latter he assumed an analogous combination of metals with the elements of carbonic acid. The principles of a new theory of acids was, therefore, included in the discussion of Davy and Dulong, but it is to be deplored that they did not follow them up sufficiently, as otherwise they might have prevented the distinction which now began to be drawn between acids containing oxygen and those which did not. With regard to Davy's attitude to the atomic theory of Dalton, it should first be mentioned that he asserted in 1809 that William Higgins was the originator of this doctrine. The latter's a comparative view of the phlogistic and anti-phlogistic theories with inductions, 1789. Davy maintained, contained views similar to those of Dalton, but later he recognized Dalton's service. Davy regarded Dalton's atomic weights as simply the proportion numbers of the elements, and maintained that there was no positive basis upon which to proceed for the determination of the atomic weights. Two other investigators of this time, Wollaston and Gay-Lussac, also refused to admit that Dalton's atomic weights were really such. Previous to Davy, Wollaston had asserted that there was the chemical equivalence of the elements, while Gay-Lussac could not concede that the ratio of one element to another was fixed by analytical and synthetical determinations. His laws of combining volumes had a definite bearing on the atomic theory. However, and this generalization, along with his work in analytical chemistry and numerous researches in inorganic chemistry, rendered further notice of him necessary. Joseph-Louis Gay-Lussac, 1778-1850, was a student of Berthollet, and in 1809 became professor of chemistry at the École Polytechnique, at the same time holding the chair of physics at the Sorbonne. In 1832, he accepted the chair of chemistry at the Jardin des Plantes. Gay-Lussac was a masterly investigator, capable of the most accurate analytical work and exact in observation, and enriched chemistry with many valuable researches. Of special importance was his work on iodine and its compounds, on cyanogen, which he characterized as the first compound radical, on sulfur and its compounds, on the oxides of nitrogen, on the isolation of boron, and his conjoint investigation with L.J. Thenard, on the alkali metals, and with Liebig on the fulminates. He also introduced improved methods of inorganic and organic analysis and is to be regarded as having laid the foundation of volumetric analysis. His name is particularly associated, however, with his investigations on the combining volumes of gases. In 1805, Gay-Lussac and Alexander von Humboldt published a memoir entitled Experiments on the Ratio of the Constituents of the Atmosphere, in which they announced that they had found the volume ratio hydrogen to oxygen 200 to 100. This led Gay-Lussac to extend his investigations to the volume relationships of other gaseous substances, which are compounds of gaseous constituents, and by the close of the year 1808, he was able to announce results which showed the existence of a simple and general law. He summarizes his results as follows. Quote, I have shown in this memoir that the compounds of gaseous substances with which other are always formed in very simple ratios, so that representing one of the terms by unity, the other is 1 or 2 or at most 3. These ratios by volume are not observed with solid or liquid substances, nor when we consider weights, and they form a new proof that is only in the gaseous state that substances are in the same circumstances and obey regular laws. The apparent contraction of volume suffered by gases on combination is also very simply related to the volume of one of them, and this property likewise is peculiar to gaseous substances. End quote. This law of combining volumes is stated by Ostwald in his Outlines of General Chemistry as follows. Quote, if gaseous substances enter into chemical combinations, their volumes are in simple rational proportions, and if a gaseous substance is formed by their union, its volume also is rationally related to the volumes of the original gases. End quote. Gay-Lussac was himself inclined to conjoin his law of volumes with the atomic theory. Indeed, he recognized in it a support for the latter. A similar molecular condition was essential, however, in order that all gases should deport themselves alike toward pressure and changes of temperature, and besides, obey his law of volumes. In other words, equal volumes of gases must contain equal numbers of molecules. Gay-Lussac drew no distinction between these molecules and atoms, recognizing but one kind of final particle. Dalton opposed this reasoning and stated that he had held the same view as to combining volumes at one time, but finally saw that it was untenable. To quote from his A New System of Chemical Philosophy, at the time I formed the theory of mixed gases, I had a confused idea, as many have. I supposed at this time that the particles of elastic fluids were all of the same size, that a given volume of oxygenous gas contains just as many particles as the same volume as hydrogenous. But I became convinced that different gases have not their particles of the same size, and that the following may be adopted as a maxim, till some reason appears to the contrary, namely, that every species of pure elastic fluid has its particles globular and all of a size, but no two species agree in the size of their particles, the pressure and temperature being the same. End quote. He also maintained that gases do not combine exactly by volumes, but frequently by fractions of volumes. He said, quote, the truth is, I believe that gases do not unite in equal or exact measures in any one instance. When they appear to do so, it is owing to the inaccuracy of our experiments. In no case, perhaps, is there a nearer approach of mathematical exactness than in that of one measure of oxygen to 2 of hydrogen. But here the most exact experiments I have ever made gave 1.97 hydrogen to 1 oxygen. End quote. His argument may be illustrated as follows, taking hydrochloric acid as an example. 1 atom of hydrogen chloride consists of 1 atom of hydrogen and 1 atom of chlorine. Then, if equal volumes of gases contain equal numbers of molecules, 1 volume of hydrogen and 1 volume of chlorine should produce 1 volume of hydrogen chloride, but they really form 2. Consequently, each one of these can contain only half as many atoms as the original volumes of the constituents. Such ratiocination is manifestly conclusive as far as the theory of the volumes containing the same number of atoms is concerned, unless some different definition of atoms is assumed. The connection between Gay-Lussac's law of volumes and Dalton's atomic theory was shown by the Italian physicist Amedeo Avogadro, 1776-1856, in 1811. Avogadro discarded Dalton's artificial distinction between the ultimate particles of a compound and those of an element, and made a distinction between what he termed molecules integrants and molecules elementaires, or molecules and atoms, the former being compound particles made up of the indivisible atoms. The researches of Gay-Lussac indicate, then, that a molecule of water consists of one molecule of hydrogen and 1/2 molecule of oxygen. A molecule of hydrogen chloride consists of 1/2 molecule of hydrogen and 1/2 molecule of chlorine, and so the difficulty pointed out by Dalton was effaced from chemical literature. Avogadro's assumption that equal volume of gases, elementary or compound, at the same temperature and pressure contain equal number of molecules, although only a hypothesis, is generally referred to as Avogadro's law. It is of fundamental importance to chemistry. He also stated that the relative weights of gaseous molecules may be determined by the measurement of the relative weights of equal volumes of the gaseous substances, that is, by comparison of gaseous densities, and that the number of gaseous volumes interacting indicates the relative number of molecules interacting, and similarly, the volume of the compound gas formed, when compared with that of the constituents, gives the number, whole or fractional, of elementary molecules entering into the composition of one compound molecule. Avogadro's conclusions produced practically no effect at the time they were promulgated, and 50 years passed by before they were received with due recognition. These conclusions of Avogadro are sometimes credited to the French mathematician Ampere, 1775-1836, but the memoir of the latter did not appear until 1814, and is much less important than that of Avogadro. While Davy and Gay-Lussac were conducting their valuable investigations, an important literary chemical event, most impressive and attractive in nature, occurred when William Prout, 1785-1850, advanced his hypothesis of the genesis of the elements. In 1815, in a paper upon the relations between specific gravities of bodies in the gaseous state and their atomic weights, Prout stated that he had often observed the close approximation to round numbers of many of the weights of the atoms. From the table at his command, he further deduced that all elementary numbers, hydrogen being considered as 1, are divisible by 4, except carbon, nitrogen, and barium, and these are divisible by 2, appearing therefore to indicate that they are modified by a higher number than unity of hydrogen. He considered the other numbers might be 16, or oxygen, and that possibly all substances were composed of these two elements. A short time after, in 1816, he expressed the following views, quote, "If the views we have ventured to advance be correct, we may almost consider the proteili of the ancients to be realized in hydrogen, an opinion, by the by, not altogether new. If we actually consider this to be the case, and further consider the specific gravities of bodies in their gaseous states to represent the number of volumes condensed into one, or in other words, the number of the absolute weights of a single volume of the first matter, proteili, which they contain, which is extremely probable, multiples in weight must also indicate multiples in volume and vice versa. And the specific gravities or absolute weights of all bodies in a gaseous state must be multiples of the specific gravity or absolute weight of the first matter, because all bodies in a gaseous state which unite with one another unite with reference to this volume." End quote. Prout's conjecture was taken up by Thomas Thomson, who, being carried away by the attraction of simplicity, became the advocate of a philosophical speculation contrary to experimental facts, and even perceived in it a fundamental law of chemistry. Other chemists, too, showed a predilection for Prout's hypothesis, and notwithstanding the fact that Berzelius and Turner demonstrated its untainability. Some exact investigators as late as 1840 betrayed an inclination to some of Prout's views. In fact, some writers of the present day consider that there may be a kernel of truth concealed in it, and although it has suffered numerous reversals, it is still revived at intervals. End of Chapter 10.